one of the topics that I'm trying to, even master for my CCIE studies, because it's difficult. I think this is one of the things that, at a fundamental level, you have to know a few things, but also too, it's very fun to understand how routing works. You know what I mean? So, we'll go ahead and get started. So, chapter three, labeled fundamentals of WANs and IP routing, right? Um, for this chapter, right? The objectives that's going to be covered from the objective list is 1.0 network fundamentals. Under that is 1.1 explain the role and function of network components. 1.1.a routers, and of course 1.2 describe characteristics of a network topology architectures, and 1.2.d, which are WANs. Okay. All right, let's go ahead and jump in. So you see a figure 3-1. It's covering, showing you a small enterprise network with one leased line, right? So for a local area network or LAN, right, to connect to the internet, it needs to go ahead and use a wide area network, right? There's typically a router in place that connects that local area network to the outside world using two interfaces, right, or layer three boundaries, right? But how is the communication done? How do they connect? How do the telco companies connect them? That's what we're going to go over today, right? But in general, right, the lease line service, right? If we talk about a lease line, right, it is a physical layer service, right? It is meant to just transfer, you know, um, ones and zeros or bits from site one to site two. Okay. Speed is typically predetermined, right? You go ahead and I see my key is jumping back in. You typically negotiate that with your internet service provider, right? And of course, depending on your ISP, they'll go ahead and work out your duplex logic. So if you're using full duplex or half duplex, um, typically once you set that up, then boom, right? That lease line, right, will go ahead and be dedicated to you, right? And they'll go ahead and start transmitting that data for you, right? Because that's its primary job, to be a physical layer service, right, to the outside world, right, to other local area networks. Okay. Does that make sense, everybody?
Yeah, it does.
Yeah, yeah, it
Okay.
makes sense.
Okay.
Yeah.
Okay. All right. All right. Now, if we're looking at this, right, this diagram, it's very misleading, right? You look at it and you'll say, okay, um, how are these sites, right? Have building one and building two, how are they connected to each other? You would think by looking at this diagram, you would say, hey, there's just one cable that goes to one cable, one building to another. That's all we need, right? Well, it's not as simple as that, right? So typically, right, when one router sits, it connects to a telco, right? And that telco, it doesn't install one cable at one building and another cable to another building to connect two buildings, right? Instead, it's a large network, right? That it interconnects within its own network to connect other networks, other local area networks to other networks, right? But that network, right? That network that's dedicated to the telco, right? We view it as their own local area network, right? But from our standpoint, it is the wide area network. Okay. But how does that look, right? So let's say you know, I have site one and I have site two, right? The previous diagram, it looks like it was one cable, but no, not exactly, right? So site one, right, router one, right, connects to a switch, hear me out, underground, right? Maybe to a device on, telephone pole or to a data center that the telco owns, right? Another telco, right? That telco connects to another telco, right? Underground, right? And of course, we spoke about fiber, single mode fiber, what have you. This is how they're connecting, right? So they're connecting like this, right? All the way until we get to our second customer site, right? So this is how that lease line, um, is purchased and established and made through different sites, right? And how the telco does this. This is at a high level. There's more specifics. I do not want to make it as simple as I'm making it sound. But from a CCNA standpoint, this is how the cabling looks like, possibly looks like. Let me make sure I say the wording right. Inside of a telco for a short lease line, right? So now let's go ahead and talk about some of the different names for the lease line. So we have a circuit or a lease circuit, right? Right. The word line and circuit are often used, has synonyms in a telco terminology. Telco, by the way, is a it's used also synonymously with ISP. Okay, so just think of that whenever I'm saying telco, whenever I'm explaining your stuff. Okay. So what does circuit mean, right? Circuit makes a reference to the electrical circuit between the two endpoints, right? Okay. Another term for a lease line is a serial link or a serial line, right? The words link and line are also often used as synonyms, right? Serial in this case refers to the fact that the bits flow serially and that routers use serial interfaces. Okay. Another term for a leased line is point-to-point links or point-to-point line. These terms refer to the fact that the topology stretches between 2 points and 2 points only, right? Some older lease lines allowed more than two devices. Um, T1s, right? I'm sure you guys heard of this before. This specific type of lease lines transmits data at 1.544 megabits per second. Okay. All right. Um, and also another different name for a lease line, WAN link or a link. Both of these terms are very general with no reference to any specific technology. Private line, right? This term refers to the fact that the data sent over the line cannot be copied by other telco customers, so the data is private. All of these mean the same thing as a lease line. Okay. All right. So take a screenshot, do what you have to do. You have to know this for your exam. Okay. So I know we spoke about we saw a few figures and of course in the previous chapters about layer one, right? And we spoke about earlier in this presentation that the WAN, right, ISPs or internet service providers, they're providing a physical layer for you to connect to other local area networks, right? But how is that done? Right? How is that done? Right? So that lease line provides a layer one service, right? And what it's saying is if Donovan, right, he gets a contract for a lease line, right? What that what the internet service providers are promising Don, right, for this lease line is I promise to deliver bits between the devices connected to the lease line to other local area networks. Okay, right? But the key thing is, right, how I transfer this data, right, is different, right? So in the local area network, right, my how my frames look at layer two and and how it looks at layer one, how my packets look at layer three is entirely different whenever I'm transferring that data via a lease line, right? So instead of using general layer two headers and trailers or what have you, what a lease line, right? And this is just for the exam, right? This is not everywhere. So please take note of that, right? Typically, the routers would go ahead and use two data link protocols to transfer data on wide area network lease lines. One is HDLC, high level data link control, right? That's one protocol at the data link layer, or point to point protocol, so PPP. Okay. All right. So we can see here, right, figure 3 and 4, that it shows you the structure of an HDLC frame, right? So we have our flag, we have the address, we have the control, we have the type, and we have the data, and we have FCS. FCS should be familiar to you, right? But all data link protocols, they perform the same job to control the correct delivery of data over a physical link of a particular type. Okay. All right, for example, right? So Ethernet data link protocol, right? It uses the destination address, right? Using the destination address field to identify the correct device that should receive the data and an FCS field that allows the receiving device to determine whether the data arrived correctly, right? Again, remember what I said, an Ethernet data link protocol. Now let's go ahead and shift gears, what we just talked about. The WAN data link protocols, HDLC and PPP, provide similar functions, right? But the thing is, the two protocols that I just named for layer two for WAN technologies, right? They got to do a little bit less work than Ethernet, right? Reason being because of one, point to point, right? It's a simple topology. One side is connecting to one side, right? And that's just for that lease line, right? HDLC, right? It has some of the fields similar to Ethernet, but again, it has less fields within it. Okay, so let's go ahead and go over some of that within table 3-3, right? Comparing HDLC and PDP header fields to Ethernet, right? So flag, right? So we have our flag, right? The Ethernet equivalent is preamble and SFD, right? What does that mean, right? It lists a recognizable bit pattern so that the receiving nodes realize that a new frame is arriving, right? Let's talk about address, right? So HDLC and PPP field have an address field, right? The Ethernet equivalent is a destination address, okay? Identifies the destination device, but not interesting for lease line point-to-point topologies, okay? We don't see source address here, right? Within that frame. So let's keep going, right? We have a control, right? Ethernet equivalent is not applicable. Hopefully I said it right, right? What that means, of course, is no longer of use today for links between routers, right? So this isn't even used. We can go ahead and cross that out, right? I know you guys are probably thinking, well, why is it on the exam? It has to be on the exam because it's still being used in some places, right? So you have to know what that is, okay? Let's talk about type, right? Type, of course, still exists within Ethernet, right? It identifies the type of layer three packet encapsulated inside the data portion of the frame. Okay. And last but not least, right, they still share FCS, right? Which its job is to identifies a field used by the error detection process. It is the only trailer field in this table. And guys, as a quick refresher, right? I want you guys to remember FCS is not error correction, it is only error detection. Okay? Any questions? All right, let's keep rolling. All right. So, what is the IP routing logic, right? Let's walk through it, right? So we have PC1 and it wants to talk to PC2, right? Right? So let's go through these steps. PC1's network layer IP logic tells it, right, or its IP stack on its PC, tells it to send the packet to a nearby router to R1, right? The destination is the goal. The goal is to send it to PC2, but first it needs to go ahead and send that traffic to a nearby router, right? That's the network layer logic, right? We get to step two, right? Our router R1's network layer logic tells it to forward, aka route, the packet out the lease line to router R2 next, right? So R1 is going ahead and passing that traffic that's coming from PC1 over to router 2 within its wide area network, right? So it's sending over to that there so it can get to PC2, right? Then we go ahead and look at step three. Router R2's network layer logic tells it to forward or route the packet out the LAN link to PC2, right? Simple enough, right? All right, we have a LAN, we have a WAN, and then we have a LAN, right? And of course, you can see, hey, final destination is PC2, send it to R1 next. So I'm sending it to the next hop, right? And we look at step two, hey, final destination is PC2, right? My internal workings, right? my forwarding information base, and we'll get to that in the future, right? Along with my routing information base, right? Looking up through my ARP table, I know if I want to get to PC2, I need to go ahead and send it to R2 next, right? Then I do the same thing in step 3, right? Final destination PC2 on R2. Excellent. Send it to PC2 next. So I go through the ARP table, I go through my forwarding information base, my routing information base, aka my routing table. Boom, it gets to PC2. Okay, right? All right, but let's go ahead and talk about um let's talk about in detail what it looks like, right? So we got the same diagram, PC1 and PC2, but let's say we're using HDLC. We've been talking about that, right? So let's follow these steps through this figure, right? So step 1, right? We're at LAN 1, we're at PC1, right? From PC1, let me go ahead and get my handy dandy pencil, right? We're sending this frame, right? 802.3, so Ethernet, right? To send the IP packet to router 1, right? To router R1 next, PC1 encapsulates the IP packet in a Ethernet frame, right? That has a destination MAC address of R1, right? So he's sending it, he wants to send it over here. But first, he has to send it here, right? Reason being, right? And we'll talk about that in the future, is because of ARP, right? Because of course, what they call a default gateway, right? And we'll talk about that in the future. But that's where the destination MAC address is for his next hop, right? That he needs to send it to before he can get it to PC2. Okay, let's look at step 2, right? Router R1, right? So we're right here, de-encapsulates. Okay, so we're gonna take the Ethernet header and trailer off, right? So it's removing, de-encapsulates the IP packet from the Ethernet frame, right? Then it encapsulates, boom, right? It inserts the packet into an HDLC frame using an HDLC header and trailer and forwards the HDLC frame to router 2 next. Okay? All right? That packet didn't change. So layer 3 is still fine. But from a layer 2 standpoint, right, it's going to change with each layer 3 boundary. I'm going to drill that into your heads. That is always going to be the case. At every layer 3 boundary, right? Layer 2, right? Layer 2 will always change. Okay? Keep that in your heads, right? So, like I was saying, step 2, router 1 de-encapsulates or aka removes the IP packet from the Ethernet frame coming from the LAN 1. It encapsulates, leaving LAN 1 and going into the wide area network. It encapsulates, inserts the packet into an HDLC frame using an HDLC header and trailer, and forwards the HDLC frame to router 2 next. Okay? Right? Then we go ahead and get to router 2, right? Router 2 de-encapsulates, right? The same thing happens, removes the IP packet from the HDLC frame, right? And encapsulates, insert that packet into an Ethernet frame that now has a destination MAC address of PC2 and forwards that Ethernet frame to PC2. Okay. So this is the general concept of routers de-encapsulating and re-encapsulating IP packets. Okay. So that MAC address is never going to be the same. Let's say if you want to go to, you want to visit google.com, you want to visit YouTube, right? That IP address might be the same, right? But the MAC address will always change per layer 3 boundary or per hop. Okay. Does that make sense?
Yes, it does.
Okay. All right. Let's go ahead and move forward. Okay. So let's talk for a little bit about Ethernet as a WAN technology. All right. So for a while, right, and I think we've talked about it so far, is that you would only see Ethernet technologies only for local area networks, right? Why is that? Right? It's because, of course, Ethernet, um, you would see it have, if we're talking about copper or what have you, right? Just an example, right? There would be restrictions on cable lengths, right? So I know from memory, right? Copper has a restriction of 100 meters, right? So of course we couldn't use we couldn't use copper and what have you or Ethernet technologies for long distance, right? Um, and of course we would have to use fiber to stretch out a local area network that's using copper. Um, Past some kilometers or what have you, right? To support maybe a campus, right? A campus site. Maybe you're working at a university or what have you, and you have several buildings. We go ahead and use that, right? Um, Moving down the time of history, right? The IEEE, they improved Ethernet standards, right? And they made it to where Ethernet was reasonable for WAN technology, right? So what do I mean by that? Right. So I just spoke about fiber, right? And so, for example, right, we talked about the different names for fiber, right? So single mode fiber, right? That type of cabling, it can support 5 kilometers in length, right? For Ethernet. Okay. Um, and of course, it can even expand even longer. There's different type of single mode fiber technology that can support even 70 kilometers of a cable length, right? This is still an Ethernet technology. Okay, whenever we talk about fiber as well, right? Um, but at the end of the day, it's still fiber Ethernet. It's still a fiber Ethernet link, right? And then over time, it said, okay, we can go ahead and use this as a WAN technology, right? So now a lot of you guys, and of course my internet service provider, right? They offer WAN services and stuff like that by taking advantage of Ethernet, right? So you'll see Google Fiber, you'll see I think there's some other companies that offer fiber and whatnot, but there's many Ethernet WAN services, right? They just have different names, right? But they all use this same type of model, right? Is expanding, right? Expanding a network using Ethernet technologies, right? So, of course, in this picture, right, what do we see, right? We see Ethernet being used between two sites, right? Between the customer site and, of course, the internet service provider's network, right? And we're connecting these two sites, right? So R1 and R2 is connected, right? And we have that fiber Ethernet access link to that service provider's POP, right? So, right, what does that mean, right? And this is where, of course, I want to make a quick point to we need to slow it down and take a look at something, right? Ethernet WANs create a layer two service. Okay, I know we spoke about earlier that, of course, it's the main jobs of WAN was providing a physical layer for local area networks, but more specifically, Ethernet WANs create a layer two service, right? So what I mean by that, so when I was reading the CCNA, it said that Ethernet WANs services include a variety of specific services that vary in ways that change how routers use those services, right? What does that mean, right? So from a logical standpoint, right, it behaves as we're using Ethernet wide area network, right? From a logical standpoint, it behaves like a point-to-point connection between two routers. Okay. From a physical standpoint, it behaves as if a physical fiber Ethernet link existed between the two routers. Okay. All right. So the CCNA, it describes, right, what I just said, right, with these two, I'm sorry, with these two main overarching services, right? But in total, the different types of links, right? So, key topic here, pay attention. Ethernet WAN, a generic name to differentiate it from a Ethernet LAN. Okay, right? Ethernet point to point link, a term that emphasizes the topology of a typical Ethernet WAN link that has exactly two endpoints, the router on the two ends of the link. Okay. All right. So if your if your modem, right, which of course is customer provided equipment, is connecting, right, um, connecting to the wall or what have you, maybe to your line outside, it's connecting to that provider equipment. That is an Ethernet point-to-point link. It is using an Ethernet WAN technology. Okay, right. So that's when you would use the term Ethernet point-to-point link. Okay. From a physical standpoint, from a logical standpoint, Ethernet point-to-point link would be site one to site two. Okay. All right. Let's talk about Ethernet line service, E-line, right? A term from the Metro Ethernet Forum, MEF, right? For the kind of point-to-point Ethernet WAN service shown throughout this book, right? And I'll show you guys some diagrams that I pulled from the book, what have you, and some of the stuff that you guys have seen, right? And if you guys have experience with working with E-line, of course, MPLS, please feel free to speak up. I haven't had the pleasure, I think that's beyond my time of working with MPLS, right? But let's go ahead and go over it, right? So Ethernet over MPLS, right? A term that refers to multi-protocol label switching, right? Technology that can be used to create the Ethernet service for the customer. Okay. And remember, this is a key topic. So all four of these definitions you will need to know, right? So let's imagine real quick. We got two routers, right? Single Ethernet connection, Ethernet link between two routers, right? And this is essentially what an Ethernet WAN is, right? That's all it is. It's we're using a Ethernet link to connect to two WAN routers. Okay. Ethernet WAN. Okay. All right. So you guys are probably thinking, well, okay, I get from a layer one standpoint how it connects. How is that data traveled, right? How does that data is the layer two header and trailer, does it change, right? Now that we're using Ethernet, are we going back to 802.3? Is it still HDLC? Is it point to point, right? What's happening, right? So let's talk about it, right? I'm sure you guys already see just looking at this that something has changed in the middle, right? In the Ethernet WAN, right? So from LAN one, let me get my pencil, right? Ethernet LAN, we still are using 802.3, right? And what's going to happen is PC1, right, is going to send that IP packet. It's going to say, hey, I want to get to my final destination is PC2, right? But before I can send it to PC2, I need to send it to router one, right? PC1 is going to go ahead and encapsulate, right? Encapsulate this packet, right? Leaving its PC, inserts the IP packet inside an Ethernet frame that has a destination MAC address of R1, right? So I'm going to say, hey, I got to send this to you, but I ultimately want to get over here, but I know I have to go through you. Okay. Router one, right? We've seen other router ones before, but router one is going to go ahead and de-encapsulate that and say, hey, thanks for sending this to me. I'm going to go ahead and send your packet that has your data along the way, right? So I'm going to take off the layer two headers and trailers, going to de-encapsulate, and I'm going to insert, right, a header and a trailer, right? In my header, I'm going to have a source of the router one gigabit 0/1's MAC address. This is very important. Okay. And then my destination is going to be R2's gigabit 0/0 MAC address. And I'm going to forward that frame over my Ethernet WAN service to R2, my Ethernet WAN service, right? So 802.802.3. Okay. Same technology, right? At a fundamental level that I'm using within my local area network. Then the same thing. I'm going to go ahead and de-encapsulate here. Okay. And I'm going to go ahead and re-encapsulate, right? Because I see the destination, right? And I'm going to say, hey, I know my source. Based on my routing table, my forwarding information based on my ART table, I know where to send it, and it's going to go ahead and send it. Okay. All right. And that is how routers route IP packets using Ethernet WAN links. Okay. Any questions? Okay, let's keep going. All right. The next thing we're going to talk about is an overarching term, which, of course, one of the main um, parts of this is some of the routing steps that was happening within that Ethernet link, right? We talked about it a little bit, but we're not going to go in depth. I really want to jump on IP routing, right? Of how, from a layer 3 standpoint, how that forwarding logic is done. Okay, let's talk through this, right? So we have PC1, right? It's saying I want to send this to my destination, right? How do I make my path selection? How do I know where to send this? Right? We're going to get to that in the further chapters, right? But it knows if we're looking at PC1, get my pencil again, right? My destination is in another group, right? We said this before. We said this a little bit of time before. My destination is in another group, okay? It's in another subnet, right? Send this to the nearby router, right? Because its job is to route packets, okay? So PC1 is going to send that IP packet over to R1, right? And we'll talk about the details later on, okay? R1 is saying, hey, from a path selection standpoint, right? Using its forwarding logic, my route says send to R2. Based on this IP packet, I'm going to go ahead and encapsulate, de-encapsulate, and encapsulate this packet, right? And send it to R2. R2 is going to say, hey, I still have forwarding logic to do, right? I'm looking at the IP packet that I was sent, and I'm going to say, hey, based on what I see in the IP packet, my route says to send this to R3. I'm going to do the same thing. Okay, right? R3 is going to go ahead, look at the IP packet that it receives. Sorry, guys, for my chicken scratch. Hey, my route says send directly to PC2. Then it's going to go ahead and de-encapsulate and encapsulate and send it to PC2. Okay, this is network layer routing, aka forwarding logic. Okay, let's keep going. Right. So let's talk about what this looks like as far as how this forwarding logic is used within local area networks and wide area networks. Right. So key topic for your exam. Let me know if you guys can't see it, if I need to adjust the slide. Right. So we talk about encapsulation and de-encapsulation a lot, right? But what is actually happening? So step one, the data link frame check sequence field is to ensure that the frame had no errors. If errors occurred, discard the frame, right? This is what's happening at the data link layer, right? Whenever we're using our forwarding logic, right? Assuming that the frame was not discarded at step one, discard the old data link header and trailer, leaving the IP packet with that router, right? The router is then going to say, step three, compare the IP packet destination's IP address to the routing table, right? So the router is going to say, I see the destination IP address within this packet. Let me see if I see this within my routing table, right? If I don't see it, if I don't see a match for it, it's still my job to find the route that best matches the destination address, right? So this address will sometimes identify within your routing table has the outgoing interface of the router or possibly the next hop router IP address, right? AKA your default gateway, right? Or your default route. Okay. Then what your router is going to do, what you guys seen, it's going to say, hey, I know where to send it based on my routing information base or my routing table. And now using my forwarding information base or my forwarding table, I'm going to go ahead and I know where to send it. And I'm going to go ahead now encapsulate the IP packet inside of a new data link header and trailer for the appropriate outgoing interface and forward the frame. Okay. I'm not going to go through this because we've seen this time and time and again, so I'm not going to repeat it for you guys. Right? So, couple of things. I think I spoke about layer 3 boundaries and stuff like that. We'll talk about whenever we get to part 4, we'll talk about IP addressing and subnetting, right? Um, Now I know within this chapter we spoke about you guys saw a couple of IP addresses, but there's some foundational rules that I need you guys to remember and to take note of for the exam. Okay. Some foundational rules of subnetting can be summarized as this: two IP addresses not separated from each other by a router must be in the same subnet. Okay. The book says group. I like to keep it at subnet. Okay. So two IP addresses not separated from each other by a router must be in the same subnet. Two IP addresses separated from each other by at least one router must be in different subnets. Let me go over this again. Two IP addresses not separated by a router or a layer 3 boundary are in the same subnet. So if I have one IP address, 192.168.1.5, and another IP address, 192.168.1.6, what does that mean? They're in the same subnet. But if I have two IP addresses, 192.168.1.5, and a second IP address, 172.16.1.6, right? They're separated by at least one router, aka one layer 3 boundary. That means they are in different subnets. Does that make sense? Okay. All right. So, with that being said, if we're talking about the IP header within a packet, and by the way, this is a screenshot from the book, but you can actually look at this within packet tracer. I know some of the labs and building servers get expensive, but within you can see this within packet traces. So don't fret, don't feel like you have to spend money on a whole server to look at, packet captures and whatnot. And there's actually a free site where you can look at packet captures. I'll send that to you after this. It should be on Wireshark's website. But the IPv4 header, right, is organized, has 4 bytes wide for a total of 20 bytes. And within it, it has a source IP address and a destination IP address. So if you're ever doing a packet capture or a TCP dump, you should be able to see a source and destination IP address along with other things. Okay. All right. We spoke about the, you know, we spoke about routing and what have you. But um, let's talk about how IP routing protocols help IP routing, right? So, what do I mean by that? I didn't say dynamic routing protocols. I said IP routing protocols, right? So, forwarding logic, right? Um, for route in at the fundamental level, for routing logic to work on both, not just routers, right? Not just routers, but routing logic needs to work on both the host, your printers, your PCs, or what have you, right? All of them need to know about TCP IP internetwork, right? Or networking, TCP networking, TCP IP networking. They have to know about that. They have to have that technology on their device, on that host. Okay. So, what do I mean by that, right? So, hosts need to know IP address of their default router so that the host can send packets to remote destinations, right? Routers, however, needs to know routes so they forward these packets to each and every reachable IP network and subnets, right? So how do we do that, right? So the book explains, right? If you read chapter 3, the best method for routers to know all the useful routes is to configure the routers to use the same IP routing protocol. What routing IP protocol, right? If you enable the same routing protocol on all routers in a TCP/IP internetwork with the correct settings, the routers will send routing protocol messages to each other. As a result, the routers will learn routes for all IP networks and subnets in the TCP/IP internetwork, right? You guys are probably thinking, "What are you talking about? What are the protocols, right? What are you talking about, right?" It's a plethora of protocols and routing protocols, right? Um, it's a way to learn routes, right? We're talking about dynamic routing protocols. It's a way to program routes, right? It's a way of forwarding, right? A way of talking to each other, IPv4, IPv6, right? A lot of these different routing protocols have differences, right? We're talking about OSPF, talking about egrep, we're talking about static IP addressing, we're talking about IPv4 versus IPv6, right? All of these things are used, right, to go ahead and be an assistance to IP routing. All of this is needed, right? Let me go ahead and take this away, right? And what do I mean by that? Let me go ahead and get this, right? So each router, right? If we're talking about how this routing logic works, right? Each router, it's independent of the routing protocol, adds a route to its routing table for each subnet directly connected to the router. I'm going to say that again. This is a key topic. Each router, independent of the routing protocol, so we don't have a routing protocol on there, right? So no, no dynamic routing protocol, nothing static. We just have IPv4 and IPv6 addresses. Okay. Anytime you configure that, let's say DeMarco configures IP addresses on his router, right? Within your routing table, right? Your router is going to go ahead and add a directly connected route to the router's routing table whenever you configure an IP address. Okay. Step 2, each router's routing protocol, let's say now DeMarco does implement a routing protocol, tells its neighbors, right? Well, now we're using, let's say, OSPF, one of my favorites. It's OSPF, right? It tells its neighbors, right, about the routes in its routing table. See, because DeMarco only configured IP addresses. So now he only has connected routes. But let's say we're using a dynamic routing protocol, OSPF, that one OSPF, router is going to talk to its neighbor and say, hey, within my um within my routing database, I have these routes. I'm going to go ahead and share it with you. And the only routes that I have are directly connected routes, which are automatically installed when I configure IP addresses on my router, right? Step 3, right? Each router's routing protocol listens to messages from neighboring routers and learns routes, with the next hop router of the route typically being the neighbor from which the route was learned. I'll say it again. At the end of all of this, at the end of step 1 and step 2, each router's routing protocol listens to messages from neighboring routers and learns routes, with the next hop router of that route typically being the neighbor from which the route was learned. Okay? Right? So this is how, you know, IP routing is supported by using different IP routing protocols and different technologies. Okay. So that was a brief glimpse how routing protocols work, right? You can see the diagram, of course. This is an example of how, and of course, I didn't write on the screen. I do apologize. This is how routing protocols advertise itself about networks and subnets. But you can look at the diagram all day. I would feel better. We actually go through a lab and configure this. So we'll have our day where we have our fun. We'll actually do that on Sunday. Okay. So Let's keep going. Right. So we spoke about IP and we still spoke about some other stuff. Um, but we didn't talk about some other, you know, network features that actually help out. And some of the things that you have to know and understand, and I'm still trying to get a grasp of and learn to this day, right? Some of the three topics that are at the end of chapter 3 that are covered are domain name system, DNS, right? Address resolution protocol, right? ARP, and ping, right? So at a fundamental level, right? Let's talk about DNS, right? Can you imagine if you were trying to reach resources like YouTube, like Google, or what have you, that you had to know, especially within the cloud age now, if you get to know each and every IP address, that'd be exhausting. I don't think our computers, they probably can build something, but our computers wouldn't remember all these addresses, right? So thankfully, the IEEE, they said, you know what? Within TCP/IP, I'm going to go ahead and find a way to define, right? To define and to use host names, right? It has to be a way so I can use host names to identify other computers. Google.com is a host name for another computer. Okay. YouTube is a host name for another computer, right? But how did I learn that host name, right? How did I get to that point, right? Well, what's happening is whenever you type in google.com, your PC doesn't send an IP packet with the destination IP address, www.google.com, right? It sends an IP packet to an IP address used by the web server for Google, right? But TCP/IP, right? TCP/IP stack on your computer needs a way to let the computer find the IP address used by the listed host name. Hey, in this example, google.com, right? That method is called DNS, right? It's called DNS, right? So if we're looking at this example, right? So let me get my handy dandy pencil. We have PC 11, all right? And we're trying to reach server one. Server one will just think in your mind, this will be Google, right? Google.com, right? So Donovan, he goes ahead and puts in his browser google.com, right? By default, right? Our PCs use a TCP/IP stack, so they mainly talk via IP addresses. But we can use a DNS, we can use domain name system to go ahead and let that resolve that host name to an IP address, right? So I get on the browser, right? We go ahead and type in, hey, google.com, right? DNS is going to say, hey, I can resolve that. Here's an IP address for that, right? Because that's what your PC needs. Within the IP routing forwarding logic, it needs an IP address. It doesn't need a host name, right? The host name is just for us because we're not going to remember all IP addresses. The host name is for us. Our PCs need IP addresses. So domain name system is that middleman, right, to go ahead and do that. So it's going to go ahead and send that, right, send that IP address, and then it's going to go ahead and forward the IP packet to the destination, right? That's at a high level of what a basic DNS name resolution request looks like. Okay. You can get real in depth in the weeds. I just shared something with Donovan and Mike Hevia about and some other cats about DNS to make our lives easier because that's what it's doing. It's making all of our lives easier. So just take note of this. This diagram and of course the DNS section in general within this chapter will be on the exam. So please make sure you read it. It's a quick excerpt. It's not long, right? Let's talk about art. What is it, right? So we talked about PCs sending traffic to a remote destination, okay? But it first needs to send it to its okay. Sorry guys, the Knicks won. I'm excited. Playoff time. Anyway, we beat Detroit. So getting back to everything, right? So if I'm trying to send from PC1, send traffic to PC2, I can make that my layer three destination, right? But I first need to send it, right? I need to encapsulate that packet within layer two, right? To do that, how do I do that, right? Well, for Ethernet interfaces, right? For a router to know, or for a PC or a host to know what the MAC address is, right? How to use destination, it uses ARP, right? That's a little bit of a high level explanation. Let's go a little bit deeper. So on Ethernet LANs, right? Whenever a host or a router needs to encapsulate a IP packet in a new Ethernet frame, the host or the router knows all the important facts to build the header, except for the destination MAC address, right? The host knows the IP address of the next device. Stay with me. It knows the IP address of the next device, either another IP address host or the default router IP address. It knows that, right? So if I'm PC1, I know my default router IP address. I know where I want to send my packet, but I also know my destination doesn't live on my subnet. So I need to send it to my default router, right? Or my default gateway, as we all know of, right? I know that IP address, right? So my PC knows that, and it needs to have a way of knowing where to send it via layer two, right? Before it sends it to its layer three destination, right? Which would be PC2, right? So this is where ARP would come in. And the IEEE, the guys who went ahead and made up TCP/IP, they define ARP as address resolution protocol, right? Has a method by which any host or router on a local area network can dynamically learn the MAC address of another IP host or router on the same lane. That IP host being a printer, scanner, phone, IoT device, PC, whatever, right? It is going to use ARP to dynamically learn the MAC address of another host or a router on the same local area network. Okay. So what does ARP look like? Right? What does that look like? Right? ARP defines a protocol that which includes a ARP request, right? Which is a message that makes a simple request. If this is your if this is your IP address, okay, please reply with your MAC address. Okay. Then ARP also defines the ARP reply, right? Which indeed lists both the original IP address, right? And the matching MAC address. Okay. Once it does that, right? ARP is now resolved, and I can go ahead and encapsulate my packet and forward it to the next layer two hop. Does that make sense? On your Windows PC, you can go ahead and look at your ARP cache by typing in ARP dash A. I apologize. Hopefully this makes sense of how ARP works. Okay. And of course, if I didn't do a good job, you guys can always reach out. I'll provide other resources. Okay. All right, let's move on. Last one, and then we're done. Right. So after all the great things that we talked about, right? One last thing, right? You've deployed a network, right? We stood up all of these devices, routers, switches, hubs, put in Ethernet cables. We used fiber, we used copper, what have you. But how do we test it, right? We need a way to test basic layer three connectivity, right? Without relying on any applications to be working, right? How do we do that? Well, right? The primary tool for testing basic network connectivity is the ping command, right? So ping, and I want to make this specific distinction because this is going to be on the exam. Ping uses Internet Control Message Protocol. Okay? It uses Internet Control Message Protocol, so ICMP. Sending a message called an ICMP echo request, right, to another IP address, right, and that computer with that IP address should reply with an ICMP echo reply. If that works, you should successfully tested your network. You have IP connectivity or you have network connectivity, right? So once that works, once that ping test works, what did you confirm? What did you verify? You verified if we're using the OSI model, layers 1, 2, and 3 are confirmed and works. Okay? Remember that. All right. So with that being said, you guys are done. Any questions? I know that was a long chapter.
No, that's good. That was good. I don't have any questions though.
Okay. Okay.
Appreciate
Anybody
it, Dave.
else? Everybody all
David,
good?
um, just the last one, ping.
Yeah. Yeah.
Um, so it tests the layer 1 and 2 and 3, is it right?
That's correct. That's correct.
Okay.
And so, Gary, that is a good question. And I'm glad you asked, right? I'm going to give you some clarity. So let's say from your PC, you're using ping, right? You're using the ping command to ping Google. If our PCs are using the OSI model, well, on our PCs we have the TCP/IP stack. If every time we send out data out of our PCs, it's encapsulating that traffic, correct?
Yes,
So if we're encapsulating that traffic, right, before layer 3 comes layer 2, correct?
that's right.
And before and after layer 2 comes layer 1, is that correct?
That's true. Yeah.
Right? So that means from a layer 2 standpoint, right, I need a source MAC address and a destination MAC address. And then from a physical standpoint, I need a physical medium to transmit those ones and zeros, those bits across that physical medium to get to my destination via layer 3. So that packet that I sent needs to be de-encapsulated the same way it was re-encapsulated. So if I'm able to ping across, that means layer 2 and layer 1 can be confirmed as working.
Beautiful.
Because layer 3 needs to go through layer 2 and layer 1, right? From its own PC to the remote PC.
Thank you.
No problem. Does that make sense?
It does. I had some conversations with other colleagues, and
Okay.
I mean, ping is the only tool that I bring up very quickly because it kind of gives me the ability to test the connectivity and some other functionalities, right? Like layer 2 or layer 1.
For sure.
I got into debates that ping is not the best tool, but if it is not, then what else?
And that's debatable, right? But then you need to take a step back and say, which I struggle with when I first started getting into networking, is what is the problem we're trying to solve?
Yeah.
Right? Is the problem we're trying to solve at layer 7, or is the problem we're trying to solve at layer 3? Is the problem we're trying to solve at layer 4? Is the problem we're trying to solve at layer 2? So we need to identify, again, this ping command exists at layer 3. It is meant to just test layer 3, right? So if they're telling you, right, and it took me working on TAC to understand this, and it was broken down so simply that I was just fanboying so bad. If you're saying that's a bad tool to use, right, then you don't have a clear definition of what you're trying to troubleshoot, right?
Understood. Okay.
Because Ping's job is to just test layer 3 connectivity, right? But with testing that, it's going to confirm also layer 2 and layer 1 is working, right?
Yes.
But if other issues are not working, let's say end users are unable to reach Google, maybe you're able to ping it, but you're not able to, if you type in the address, the fully qualified domain name within a browser, it's not resolving. Then we have a DNS issue, right?
Mm-hmm.
But this is why, right, from the CompTIA Plus, right? That's why we have a troubleshooting methodology. We need to test everything. But I would tell you every day of the week, every morning, every night, ping is an amazing command to use. That's your starting. You always need a starting point to find out the root cause of something. Okay.
Okay. I appreciate that, and I've said it because I'm working on a problem with the application team.
Mhm.
It's about the slowness. They say their application slows
Mhm.
at a certain point of the time, and I'm trying to prove out that this is not network. We went in so many tools like to the NetScout and all of that, like
Yeah.
Jazz, which I
Yeah.
don't really understand a lot. But again, I felt like using like a ping to start off was very good. But when you said like defining which layer is the problem,
Yeah.
that really actually helps me now to take my problem to a little different angle.
Yeah.
Mhm.
Yeah.
But I appreciate you going over this one. I really appreciate understanding that checks all three layers.
My pleasure.
1, 2, 3.
My pleasure.
Yeah.
My pleasure. All right, guys. I'll go ahead and end this session, and I'll upload it to YouTube shortly. You guys have a great night.
All right, too. Appreciate it, Dave.
All right, guys. Later.
Everyone, Sunday.
Thanks, Dave.